In example 5.3, we look at how this probability formula can be applied. So think about on a football team, you have 11 players, and suppose for this particular team, a member of the offense is going to call the coin toss at the beginning of the game. Now there's 5 linemen out of those 11 players on offense. So what's the probability that a lineman is selected to call the toss? So we're looking for the probability of linemen. And so we need to know how many linemen there are out of how many total we have. Well, there's 5 linemen, 11 total, so our probability is 5 over 11. Now, the relative frequency approach to probabilities is similar to the classical approach to probability. However, with the classical approach to probability, we were looking at the sample space and we were determining the outcomes in a particular event out of that sample space. When we're looking at the relative frequency approach, we're going to use a set of observations. And based on those observations, we're going to be able to determine the probability. So the probability from a relative frequency approach is you take the number of times E actually did occur out of your observations, and you divide by the total number of observations that there were. Now, just as a note here, that the relative frequency approach to probability is based on these observations. And because of that, you can use a relative frequency approach to any situation. And that's important because with the classical approach to probability, the outcomes in the sample space all have to be equally likely. And there's plenty of situations where the different outcomes are not equally likely. So we will end up using the relative frequency approach when we're looking at real data sets. If you have outcomes that are equally likely, then you can use either approach to probability. Let's look at example 512. So here a professor assigns 5 problems to be completed as homework, but at the next class meeting, 2 of the 5 problems will be selected at random and collected for grading. Now you've only done the first 3 problems. So we want to look at the sample space for this chance experiment of which 2 problems the professor is going to choose. So I'm going to write out the different problems as letters just because I find that a little bit easier when dealing with probability. So there were 5 problems labeled A, B, C, D, E, and they're going to select 2 of them. So we need to make all of the pairs possible. I tend to start with my first letter and then go to the next one and keep with that first letter and go down the list. So A can be paired with B, C, D, or E. So now I've done all the pairings that involve A. Now I go to B, and I don't have to do the BA because this time the order, it's not like it's two dice or anything like that. So I don't have to do BA. I've already done that. So I'm going to go to BC, BD, and BE. And now go to C, go down that list. I can do C with D, C with E, because the other pairs with C have already been made. And then the last one is going to be D with E. So you see here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 outcomes out of the way that this can be chosen. So are the outcomes in the sample space equally likely? So here, all of these are going to be equally likely because the professor is just randomly picking these 2 problems. There's not a pair that's more likely to occur than another one. So what's the probability that you'll be able to turn in both of the problems selected? So let's decide which problems you've completed. You've done the first 3, so that's A, B, and C. Which combinations have only A, B, and C in them? We have one here, and one there. And that's it. So if you've only done the first 3 problems, you only have a 3 out of 10 chance that you'll be able to turn in both problems selected. Now, will the probability change if you had completed the last 3 problems instead of the first 3 problems? Well, let's take a look. And while I'm erasing, what do you think? Do you think it matters which 3 it is? So here we look at C, D, and E. Which pairs only have C, D, and E in them? And it's just those 3 at the end. So it's the same exact probability. And the reason that's the case is it's just labels, and it didn't matter which one's out of there. It just mattered that you had done 3 of them. Now, what happens to the probability if you had completed 4 of the problems rather than just 3? So let's go ahead and add in B, since I'm going down the list on that one. We've already decided it doesn't matter. So I can add anything that now also has B. But I can't do anything with A. So look there, we've now risen, or this now is 6 out of 10. So doing one more problem actually doubled your probability of being able to turn in both problems.